In the first part, we looked at vector operations such as addition, subtraction, and multiplication, and how they can be useful for character rigging. And in this video, we are going to look into the vector dot product and cross product. And let's start with the dot product first. The dot product is a very useful vector operation for character rigging because it can quickly give us two very useful pieces of information. It tells us how aligned two vectors are, and at the same time, it also gives us the projection, or basically where one vector sits along the direction of another vector. If I draw two vectors here, the dot product is a projection of one vector onto another. If this vector is normalized, we can use this to calculate where it sits on this vector. But we are mostly using it to calculate how aligned they are, because if this vector is in the same direction and same length as the red one, then the dot product will return a value of 1. And if the yellow vector is at the right angle of the red vector, the value of the dot product will be 0. So this way we can easily check for whether we are pointing in the same direction or in the opposite direction, because in the opposite direction, if for instance we have another vector here pointing here, this value here will be a negative value. So if the dot product is negative, we're pointing in the opposite direction. If the dot product is 0, it's perpendicular, or it's at the right angle. And then when we are slowly moving towards 1, we are aligning with the original vector. So this is useful for all sorts of operations. And as I mentioned, if the red vector in this case is normalized, then we can also use the dot product to calculate where along the red vector the yellow vector sits, which is very useful where we have 2 points. So if we have 2 points and we have a lot of points here, we wish to know where these points are along the path of this vector, and we want to know what is the position here along this original vector. This can be very useful in character rigging as well. Let's create a wrangle here so you better see, visualize this in Houdini. I'm gonna create another add node here. Just create one point and then create the attribute wrangle. So this is dot product, and I'm gonna create, for instance, 2 vectors. Let's create another one, and this one will be along the x-axis. And to calculate the dot product in vex, we use the dot function, and we simply provide 2 vectors. So now if we look at the geometry spreadsheet, and here say dot, we see we get a value of 6. And if, for instance, if they were at the right angle, the value would be 0. If they were directly in the aligned, we would get the value of 4 because the vectors are not normalized. So let's see this. So we have the normalized vectors here. We get the value of 1. Because if we're not dealing with normalized vectors, we sort of get this distorted or skewed projections from one vector to another. So if we want to get the values from 0 to 1, we have to use normalized vectors. So now if we use the opposite direction of these 2 vectors, the value is -1. So now how do we get a vector that sits along this vector here? So we have to only use the normalized vector for this green one, for instance. So if we have like 2.1, we have this kind of projection. or I'm gonna do it like this. We just use the dot product and multiply it by the normalized version of this green vector, which now gives us the blue vector, which is the projection of the red vector along the direction of the green one. And let's change the green vector so it's not aligned with the x-axis. And I'm also going to make it a little longer. And I'm going to just draw again a little here. So what we are seeing here is simply a projection of the red vector onto the green one. This is the green vector. This is the red one. And then we have a projection here. So because we use the normalized version of the green vector and the non-normalized version of the red vector in the dot product, we get the dot product that is basically the length of this blue vector. And if we multiply this length with the normalized version of the green vector, we basically get this blue vector. So this way we can project points onto another vector. And this can be very useful character rigging when, for instance, we wish to limit certain operations just based where along this vector these points sit. So let's do that next here. I'll create a grid here. And let's place it like this. And create a little denser grid. In character rigging, sometimes, for instance, let's say a character's face, we wish to limit operations between 2 points. So this could be 2 points like the mouth corners or inner and outer eyelid, and do some deformation just between those 2 points. So this is going to be an example of that operation. And we're going to set the attribute. In this case, we're going to use color because it's easy to visualize. And I'm going to set it to black. And we're going to define 2 points. And we're going to define different color based on where between those 2 points these points sit. So I'll create another add node. I'm going to create again 2 points. And I'm going to create just a line here so it will be a bit easier to visualize what's happening here. Now, let's create an attribute triangle. And the first input, I'm going to color. The second input into the add node. Let's name this dot product color. So first we'll need to define this vector here, which is these 2 points. And then for each point, we'll create a dot product to project where on this vector it sits. And if it is outside, we will not colorize. If it is between those 2 points, we will use a color ramp parameter to colorize the points. So depending on the angle and length of this vector, we will colorize and define the attribute, which in this case will be color for these points here. So the first thing we'll need is these 2 points and the vector between them. So let's do very similar what I've done before. So the first point position, the second point position. Then we can define the direction vector, which is simply p1 minus p0. So this is in this direction here. Then we will also need the direction of the point to the first point. So point here is point position minus p0. So what we now have here is the direction vector. So the direction vector, is this one. And we also have for each point, for instance, for this point, we get this one. So this is the point direction vector. So now we will use a similar calculation as before to calculate this position here. So what we will do is simply calculate the dot product. So between the point direction, and as we learned before, we have to normalize the direction vector. Otherwise, we would get distorted or skewed projections, which we don't want. And now we can say if the dot product is greater than 0, that means that the point is not behind in the other direction of this vector. And at the same time, the dot product is lesser than the length of this direction vector. So let's create here another variable which will hold the magnitude or the length of the direction. So that means it's not behind here. So now we have just the points between the start and end position. Then we can do some operation here. For instance, we can color this differently. Or let's create this a little better to create a ramp and colorize it properly. So the ramp position will simply be fit function. So we'll provide dot product between 0 and the length of this vector and remap it to 0 and 1. So the ramp position now here, it's the value of 0, and here the value of 1. And now we can simply add another color ramp parameter. So this will be remap color. And here, let's add a few colors here, like this. And now we can set the color parameter to be this remap color value based on this ramp. So now, as we can see here, we get this kind of effect. So if we now change these two vectors relative to each other, we change the direction vector where they are, and basically we define this kind of effect. So again, useful in character rigging, where we wish to define attribute values based where along this vector points sit, and also limit the deformation just on for instance, between the start and end position between these 2 points, and based on the direction that we don't get any deformation outside of this area. So a very useful vector operation. Now just color this. And we're going to create another example here. And a lot of times we wish to drive certain deformation when a skeleton is facing a specific direction. And here a dot product can also help very much. So let's create 2 simple skeletons with 2 joints. This will be the first one. And this one will be simple the pose. And the next one, I'm going to just copy this one. This one will be the animated skeleton that we would be animating. So I'm going to create a rig pose. Set a different position here. So here we wish that when this animated skeleton is moving towards this skeleton pose, we wish to apply a certain deformation, for instance. So let's create a sphere geometry here that we will deform based on how close this skeleton is getting to this position. So I'm going to create an attribute triangle. And first input goes into the sphere, the second input into the animated skeleton, third input into the pose skeleton. So I'm going to name dot deform sphere. And here, again, we're going to create just a few vectors. So the first vector will be this one. So vector anim, going to be 0.1. So the second point is this one, the first point is here, and if we subtract, we get this direction vector. So 0.1 position minus 0.0 position from the second input. So now we have this vector, and we'll do the same for the pose vector, which is this one. All we have to do is change the point function to use the third input. So now we have two vectors that we can use for dot product. And here, when using angles, we want to use normalized vectors. So we want to normalize both pose as well as anim. Otherwise, we won't get the values into 0 to 1 range. And let's say that we will scale this. So based on how close we are, so we will just multiply the point position, because here the sphere is at the center. So if you multiply the point position, it will just move outwards or inwards. So that means that here we now, as we move away, and here we get a negative scale. So for instance, we could just limit this operation. Dot is clamp, this is the clamp function, which will just limit it to 0 and 1. So we don't get any values in the negative direction. So we get this sort of effect. So when we approach this position or this angle, we see now that we apply a certain deformation. And this is very useful in a lot of character rigging operations when we have poses and we wish to apply operations when a skeleton is pointing a specific direction, and we set up this kind of pose joints, and when the skeleton moves towards this joint, we apply a deformation, and a dot product can be used for this kind of things. So a dot product is a very simple way to check whether or not the vectors are facing the same direction and how aligned they are, which is very useful in character rigging. So I'm going to just add another color to this. And now let's move on to cross product. Cross product is another useful operation between two vectors, and the cross product between two vectors is another vector which is at the right angle to those two vectors. So let's see how this actually works in practice. So I create here another point. I'm going to create an attribute triangle. Let's call this simple cross product. And here, let's again define two vectors. So this will be the first one. Let's also define the green one. And for the cross product, we use the function cross, which takes two vectors, so red and green. And as we can see, the cross product between these two vectors, I'm going to just change these values a bit. So it's easier to see. Maybe some this. We see this vector is perpendicular to both these two vectors. And the order of operation is important for cross product. So if we change the order of operation here, we'll get a negative direction or the opposite direction, you see. So the cross product between vector r and g is the same as the cross product of the negative cross product of vector g and r. So basically, if we now set the value of b vector to be minus cross of vector r and g, so the reverse order for cross operation, the result will be the same. Yeah. So the order in which we make the cross product is very important, as it defines the direction of this vector. So this is a very useful operation, since we can calculate the vector which is perpendicular to other two vectors. And this can be especially useful when we need to calculate, for instance, the up vector. First, I'm gonna just add a different color for this one. And now here, I'm gonna create a simple skeleton. For instance, something like this. And then I'm gonna create a rig doctor to initialize the transforms and reorient the joints. Then I'll create a rig pose that will be used to rotate the skeleton. And usually we want to find the up vector by using these 3 points to define the plane, and then the up vector is perpendicular to this plane. So let's create an arbitrary triangle here. And what we will do here, we will need to define 2 positions. So the first position, or the first vector, will be this one. So this will be, let's say, vector A, and then we'll have another vector, which will be vector B. And the cross product between these 2 vectors will be perpendicular to this one. So this will be the up vector. So the useful feature here is that when we will rotate the whole skeleton, this up vector will be perpendicular to that plane. So this is useful when we want to avoid, for instance, flipping when the skeleton rotates, and we don't wish to use the world up vector, because when the vectors align with the up vector, we get a flipping and so on. So this is just a simple exercise in this. So what we will do here, define these 2 vectors first. So vector A will be 0.0, and I'm gonna just make sure that the point positions are 0, 1, and 2. So the vector A is the 0.1 minus 0.0, and then I'm going to just copy this, and the vector B is going to be 0.2 minus 0.0. So now we have vector B, and V up is the cross product between A and B. Now we hide this, and here I'm going to just add this to visualize. So now we have in the opposite direction. So let's do cross product between B and A. We have it like this. This is the up vector. Let's just normalize it. It's not so long. So as we can see, we get the up vector. So that means that if we rotate the whole skeleton here, the up vector will stay perpendicular to these vectors here. Okay, so this is another useful operation for calculating, for instance, the up vectors. I'll rename this up vector. And What we can also do with a cross product is create a direction plane when we only have a line. For instance, we have 2 points positions, and we want to define a plane that is perpendicular to this direction so that we are not moving in this direction but just around. So basically we're creating sort of a direction plane for this specific vector. So let's create another add node here and add 2 points. And let's create a vector here between these 2 points. And let's only set the group to first vector so we don't get duplicate visualization vectors. And now if we shuffle these components here, so if we shuffle the x, y, and z components and shuffle them this way, that we get z, x, and y components, we get another vector that will not be the same as this one. And then we can use the cross product to create another vector. And to shuffle the vectors in vex, we can use the swizzle function. And we'll just name this vector swizzle because we'll use the swizzle function. And we provide a vector, and then it's define which component from this vector will be the first one, which the second one, and the third one. So if we say 2, this will be the z component, 0 for previous x component, and 1 for y component. So now if you look at the swizzle direction vector, it's marker and vector. So now we see we created another vector. And if we create a cross product between these 2 vectors, so the blue vector and the swizzle vector, we get another vector that's perpendicular to these 2 vectors. And now if we create another vector that's a cross product between the red and the blue vector and hide the swizzle vector, we have basically provided 2 vectors which can form a plane that is perpendicular to the direction of these 2 vectors. So this is another way that we can position, for instance, objects on this plane without moving in the direction of this vector. So this is another useful option. Of course, when the swizzle and the blue vectors are aligned, that means that the result of the cross product will be 0. So if these 3 values are the same, such as 1, 1, 1, we will get a result from the cross product that we can't use. So we can actually do a little correction here and say if the length of this cross product, so in this case the vector r, is 0, then we can modify this swizzle vector and just set some values that are not the same, and then again create a cross product. So this way, even if the vector components are the same, we can create a cross product. And what we want to do here is use the normalized vectors in this case, because if we'll do any operation with these vectors, usually we'll want to deal with normalized vectors so that these axes are all of length 1. So let's create here the normalize, and here again the normalize. And again here for the green, which in this case it's not necessary because we already normalized the blue and the red one. So the cross product between them is already normalized. So this is another way when we have 2 points that form one axis direction, and we would like to have two more perpendicular directions or axes that we can use to form another plane and use as a coordinate system. So now when we, for instance, change this point, you always have these axes that are perpendicular to each other. So another useful feature in rigging where we wish to offset positions, but not along the axis of the main vector or joint, for example. Now let's also name this triangle. So this will be a direction plane. And let's also colorize this part of the setup. And that was an overview of vectors and vector operations that I find useful for character rigging in Houdini. So I hope this video will help you with your own character setups, and see you next time.